David, could you hear me?
Yep, I can hear you now. Sorry, my audio got all wonky for a second.
Did you receive my messages?
Hold on one second. I hear the video playing there in the background. You mind if I mute you?
Um,
Oh wait, no, never mind. Sorry, you can unmute yourself. I'm catching something on my end here.
it's fine.
That was weird. Okay, sorry about that. Ian, you messaged me over the weekend.
Yeah.
I did not
Hello.
see it.
Hello, Prof.
Hello. Hi, Mawahib. Good evening. Ian, what was your question?
So, two different things. First off, when it came to the homework, when I was answering the second question, the one with the multiple parts, after I answered the second thing on said question, I then tried to answer another thing on it, and when I got the answer wrong, it just didn't let me answer anything on the application again. So,
Okay. Stick around after class and I'll look into it.
all right.
Okay.
I have a question.
Yeah.
Hello, by the way.
Hello.
What is it? The assignment, the black body spectrum, it never opened up.
I got that information from the earlier section.
Okay.
Which is weird. I did not know that was going to be an issue. I did open it up on Blackboard, but it also needs to be opened up on MyOpenMath, and I didn't realize that was the case. So I extended it to, I just opened it up pretty much indefinitely. So
Okay.
you can go in and finish it up. Okay.
Thank you.
You're welcome. I'm very sorry about that.
That's fine.
Okay, so I actually don't have that much planned. I mean, I've got about, let me see. I've got about, well, we'll see. We'll probably be here for an hour, right? But it's not going to be a long night tonight. So let me start by getting into presenter mode, and then I can share my screen. All right, and so I'm going to start with a topic here. I'm not sure how strongly some of you might feel about this question. But the question is, what is a planet? Or what makes something a planet? And I'm just curious. I know that we're not super crazy about turning our mics on and participating, but I want to open the floor for a moment. If anybody could chime in, what makes something a planet as opposed to something else?
Mind if I?
Go for it, Ian.
So I don't know the honest definition, but I'll come up with my own. Basically, what I see as a planet is a giant, I guess, mass that goes around the sun. Maybe that's a little bit too broad.
Nope, it has to orbit the sun. All right, it's got to orbit the sun. Right, it's got to have a lot of mass, but there's something we need to add to that. Right, not only does it need to have a lot of mass, but it needs to have enough mass to make itself round. Right, so it's got to be massive enough that it can pull itself into a spherical shape. In other words, we say that it can assume a hydrostatic equilibrium. And there's one final thing. There's one final piece, and it's actually this third criterion that is the reason Pluto was demoted from its planetary status. James, what do you think?
It can't have someone else. It can't share an orbit with another planet.
Bingo. Right. It has to have cleared its neighborhood. Right. Cleared the neighborhood around its orbit. So essentially, it should be the only thing in its orbital path, only large thing in its orbital path. All right. And so Pluto is not a planet because it failed criterion 3. Right, and therefore Pluto is a dwarf planet. So if we go ahead and we look at the outer solar system, you can see here Jupiter's orbit is in the middle, or closer to the center. Then going outward, you have Saturn, Uranus, Neptune, and then Pluto. Its orbit kind of crosses over Neptune's, right? But along Pluto's orbital path, there are all of these objects in the Kuiper belt, right? Because Pluto exists out in the Kuiper belt. And so we say Pluto has not cleared its orbit. Well, then how do we classify something as a dwarf planet? Right? Because if we have criterion, if we have a set of criteria for what makes something a planet, we should also be able to differentiate a dwarf planet from other things, right? So like, well, is the moon a dwarf planet? Well, to be a dwarf planet, the first two criteria are the same, but the third criteria for dwarf planet is that it has not cleared the neighborhood around its orbit. But it's also not a satellite of something else, right? So Pluto, while Pluto has not cleared its neighborhood, it's also not orbiting another object other than the sun. So like the moon, for example, the moon orbits the sun, right? The moon orbits the sun. The moon has enough mass that it is nearly round. The moon has not cleared the neighborhood around its orbit because, well, there's the Earth. But the moon is a satellite. The moon is a satellite of the Earth, and that's why the moon would not be considered a dwarf planet. All right. And here are 5 dwarf planets in our solar system. So there's Pluto, there's also Ceres, which if you listen to the earlier lecture, is the largest object in the asteroid belt. Then there's Haumea, Eris. I'm not, I wish I knew with certainty the pronunciation of this.
Make.
That's what I want to say, but I also feel like it might be make, and I just be a fool for trying to pronounce it like that. But in any case, Pluto is the most well-known dwarf planet. So a little bit about Pluto's discovery. Pluto was kind of discovered almost by accident. You know, it was discovered by Clyde Tombaugh at the Lowell Lowell Observatory. And the way that he found it was by looking at photographic plates, right? So back in the early 1900s, when photographs were, you know, somewhat far and few between, especially when you're talking about photographing the stars, where the light is so faint, they use these plates. And the cool thing about these photographic plates is that they were transparent, so you could stack them on top of each other and see how things moved. And so, you know, you could take 2 pictures of the same spot in the sky at 2 different times of the year and notice that, like, ooh, you know, this dot used to be over there, but now it looked like it moved over here. Maybe we should take more pictures, and then ultimately find that there's an object moving across the sky. And that's how Pluto was discovered. So this picture on the left and the ones on the top here, these are the OG photos of Pluto. right? They're very, very low res. Pluto is mostly made of water ice, right? Hydrogen compound, specifically water. It's believed to have an iron, nickel, alloy, and rock core. So there is rocky and metal material out in the Kuiper belt, right? It's not like once you reach Jupiter, there's no more rock and metal in the solar system. It does have an atmosphere made of nitrogen, right? Again, it's all here, very similar to Saturn's moon Titan. And then in the past decade, a much higher resolution of Pluto was photographed. This file is so big, the file, excuse me, the size of this image file is so big that when I included it in the PowerPoint, it like more than doubled the size of my PowerPoint's data size. So here's the highest resolution of Pluto that we have. And you can look this up online and zoom in with much greater detail than I'm able to show you here. Now there are other planets, right, minor planets that are out there. And the cool thing about discovering another planet, is that you get to name it after yourself. That's kind of the greatest scientific honor, is that you get naming rights when you discover something. So for example, here's a list of names that people have given to planets that they've discovered. There is a planet out there called Tyrannosaurus. There's Tweedledee and Tweedledum. Somebody named a planet Tycho Brahe. Timothy Coons. So interesting that there are such wild names. But you can look up the history of the naming of Pluto. It's actually, I think, a fairly interesting story. And so how do we find these other planets, right? These, what's called an exoplanets. Right? How do we find exoplanets? Well, what exactly is an exoplanet? Simply put, it is a planet that is outside of our solar system, right? So exo stands for extrasolar. Right, so an exoplanet is an extrasolar planet. Extra meaning beyond, and then solar meaning our solar planetary system. So extrasolar would mean outside of our solar system. Well, there are 5 ways that that astronomers use to find planets, and we're going to talk about each one of them in detail right now. The first, and these numbers at the bottom here, it gives you a number of planets discovered using each method. I have not had time to update this in a while, but if you look on NASA's website, actually, I'm going to open it up right now and I'm going to screen share it with everyone. Hold, please. Okay, so just giving you the updates and then I'll open up each one. The radial method is now at 837 planets discovered. The transit method is at 3,333. Direct imaging is at 51. Gravitational microlensing is at 108. Minuscule movements is actually down to 1. I'm not sure how they go backwards. Seems rather odd. Okay, so let me go ahead and share this. All right, if I make this a little bit bigger, can everybody see everything? Too big, too small? Not wide enough on your screen?
Could see it.
You want me to make it a little wider? Is that better? Sorry, Ian, I was watching your hand movements. That's good?
Yes, Professor, that's good.
Thank you very much, Andre. Okay, so first, let's look at the radial velocity method. Watching for wobble. Okay, so notice how the small planet here, smaller than the star, causes the star to wobble on its axis, right? It's large enough that it can get the star to move around back and forth. I like to think of this as like, you know, when an adult is like grabbing a child and swinging them around in the air, and the adult kind of like stands in the middle, maybe has to lean back a little bit to offset the distribution of weight, and the child just sort of like swinging around the outside. That's kind of what this is, right? This is like a dance between a star and a planet, where the star is basically swinging the planet around it, and the star has to lean back a little bit, right? Now, as we're watching the star, right, from our perspective, we're gonna see the star at times moving towards us like it is here, and moving away from us like it does here. And as it either moves towards or away from us, what we see in the light coming from the star is this red shifting and blue shifting. So that was blue shift, now we're at red shift. Now we're getting more blue shift again from the star. And basically we can plot a graph over time of seeing how frequently we're switching back between red shift and blue shift, and use that to figure out, well, how quickly is the planet orbiting? How long does it take for it to complete a full cycle? You know, and from that, you know, we might get some information based on the size of the star. What would the size of the planet have to be to get it to orbit like that, to get the planet to get the star to wobble that way? And we'll talk a little bit more about these in the slides in a little bit. Then we have the transit method. In the transit method, what we see is the planet passes in front of the star, and what happens is the amount of light decreases as the object transits in front of it. So here, from this, you know, this graph will repeat itself in time, and again, we can use that to figure out what is the period of this planet's orbit. Right, we just have to figure out what's the gap between, let's say, this dip and the next time it does this. Right, we can figure out how long it takes to do a complete orbit around the star. But there's actually more information that we can get from this. Right, we can also get information about the size of this planet. Right, based on the size of the star, we can look at how much the brightness decreases by and figure out how much of the star is being covered up. And if we know the diameter or the radius of this planet, we can approximate its volume. So this is what it would look like if there's a single planet. But you know, sometimes the universe isn't that simple, right? There could be more than a single planet. There might be planets of different sizes. Right, so, and you can sort of see here, they're going around the back now. It's not always a nice small planet. Sometimes we get these big planets, and you can see the difference in their light curves. The bigger planet's going to have a larger dip than the smaller planet because more of the star's light is being blocked. But what if we have multiple planets? What is this light curve going to look like? right? That's interesting. So from this, now we start to see like it's not always like a nice rectangular drop. Sometimes we get like this almost like a skyscraper looking graph. Right, and then we can figure out maybe there are multiple planets orbiting something and what their different sizes are, the different periods of their orbits. So that's the transit method. Okay, again, so the transit method allows us to determine the size of something. The wobble or the radial velocity method allows us to determine the mass of something. Right, we could determine the mass of this planet based on how much the star wobbles. Now notice we can't use the transit method in this case, because when the planet is at its closest to us, it doesn't actually block the star, but it does still cause the star to wobble, and we can detect that. So even though it's not transiting in front, there's still a way to measure its presence. And so that's the radial velocity method. Then we talked about the transit method. And then there's direct imaging, right, which is actually taking pictures. So when when a star is blocked by something, right, if we can block out the light from the star, almost like the same way if you go out at night and there are street lamps and you can block the glare from the street lamp, you could see the stars in the night sky. But if the street lamp's on, then it's hard to see. In the same way, astronomers are going to take something to block out the light coming from a star, and that might make it possible for a planet that doesn't emit its own light, but rather reflects the light from the star. It might actually make that more visible for us, and then astronomers can take pictures of it. Okay, I'm actually going to come back to gravitational microlensing. I'm going to skip that one and talk about astrometry or astrometry. And in this case, you can sort of get the idea from this, from this video that, we're basically looking at stars as if they're on a grid and measuring how a star moves. Right, so this is almost like looking at the top-down view of the Earth orbiting around the sun. Right, so this is, from this perspective, this is almost like the same video that we watched with the wobble method, but now the perspective that we're looking at is different. So we actually wouldn't get a Doppler shift here, because as this planet's wobbling, it's not really getting, as the star is wobbling, it's neither getting closer to nor farther away from us. But from this perspective, we can see that the star does wobble by measuring its distance from other stars. And with that, we're able to get information about the orbiting planet, how big it might be, or rather how massive it might be, how quickly it orbits, etc. And last but not least is gravitational microlensing. Now, mass bends the fabric of space-time, and it's kind of what tells objects how to move through space, right? So when, like in our case, our sun warps the fabric of space-time, and it tells the Earth how to move along a curved path in a nearly circular orbit around the sun. But the interesting thing about this warped space-time is that it also bends light. It also bends light. And as a result, we get this thing called microlensing, right? Where here we have this star, and down here at the bottom, this green dot is us, the Earth. And as this star here and its little exoplanet move in front of the Earth, it bends the other light rays that are going in other directions towards the Earth. So the Earth gets more light than it normally does. So let's watch that again. All right, so at the moment that the graph peaks, you'll see that we have 3 yellow bands pointing right now. Boom, it was right at that moment where the light was bent so that these 2 rays on the side here were also focused towards the Earth. Now, because there's the exoplanet orbiting that star, you can see again, there's the star, there's that little green exoplanet. Watch what happens on the graph. All right, we get this little spike. And this spike tells us that that star is not alone. All right, it's got something orbiting around it. And we can use that to then to go ahead and take a closer look and see what we find. All right, so these are the 5 ways to find a planet. So again, with the astrometric technique, we're basically looking at a star and watching how it moves over time. It's like sometimes it's not, as I mentioned, it's not as simple as to say, there's one exoplanet orbiting this distant star. There might be many exoplanets orbiting it, just like how we have 8 planets orbiting our sun. And so we might find that the center of mass of that, of the star wobbles a little bit. We might see something like this, where like in 1960, the star was here. And then in 1965, it was here. And we can basically follow this around. And it's showing where it will be in 5-year increments. Right, and it's not always super nice and neat. Sometimes it might look a little funky, like this one does. Then we have the Doppler method, which is the wobble method, right? This is the radial velocity method, where we're measuring that Doppler shift. The exoplanet's tug causes the star to wobble, which means sometimes it might be moving towards the Earth and other times it might be moving away, and that's going to cause its light to be either red shifted or blue shifted. Right? And we can measure that very accurately. Right? We can measure blue shift within 1 meter per second of moving. Right? So stars that are millions and millions and billions of miles away, we can measure their motions to the precision of 1 meter per second. And so here's a graph of what that velocity might look like for something that has multiple planets. Right? It doesn't have to look like a nice sine curve like this one does. Sometimes it might look like this more intense repeating pattern, something with multiple planets. And if you look here on the image on the bottom right, it's showing you these 3 planets, B, C, and D, orbiting this star Upsilon Andromedae. Okay, again, the transit method. Right here, we're looking at light curves and we're basically measuring the brightness over time. How does the brightness coming from a star change with time? As the brightness is decreasing, it means that something is transiting between us and that star. We can use that to gather information about the size of planets. So here's an example of data coming from a light curve. Notice that the dip is very small. If you're actually looking at the y-axis here, the difference between 0.9996 and 1, not much of a difference. You know, this is like with, you know, 10,000th of the normal brightness, 4/10,000ths of the normal brightness. Right, but it also gives us information about whether or not these exoplanets might have atmospheres, right? So not only will we see that there's starlight that's not making its way to us, the observer, but there's additional light that is being absorbed by the planet's atmosphere. And so we can figure out, based on the light that's being absorbed, based on the specific wavelengths, what the atmosphere must be made of. And so we can really get a lot of information about these exoplanets. Right, so how are we detecting these exoplanets' presence? We can take direct images, but that's a little bit difficult because starlight's very bright. So we really need to make, you know, we got to kind of get lucky and make sure that not only are we blocking out the light coming from that star, but we're doing so at a time when the exoplanet would be visible to us. But the other way that we can measure it, or another way that we can measure it, is using the Doppler shifting, right? The radial velocity method, watching for wobble. We could be using the transit method, right? Where the planet actually goes in front of the star. And these different methods give us more information than one might initially think, right? We can figure out the mass of the exoplanet. We can figure out the size of the exoplanet, right? We can figure out information about the atmosphere of the exoplanet, right? If we can figure out the mass of the exoplanet using the Doppler method and the size of the exoplanet using the transit method, then we can calculate the density of these planets and see whether or not their densities are similar to that of Earth in our search for Earth-like planets and life on other planets. And there are some, you know, there's some interesting possibilities, because there are many star systems where there's more than one star. Right? I mean, this is just a scene from Star Wars, but you know, there are plenty of binary star systems, right, where it's two stars orbiting each other and planets that orbit them. So there are a lot of possibilities out there. All right, so to summarize, we can measure orbital properties such as period. We can measure the distance to these exoplanets. We can measure the shape of the exoplanets. We can measure the mass and size of these planets. We can, you know, measure the radial distance of these planets from the stars that they're orbiting. We can get information about their atmospheric properties, right? How hot are they? What are they made of? What kind of gases are in the atmospheres? So the search for exoplanets is a continual process, right? It is ongoing, and there are millions and billions of exoplanets just waiting to be discovered. And just think, if you find one, you get to name it whatever you want. And that is the end of tonight's presentation. All right, it is, I told you it would be on the shorter side. Actually, I was under what I thought it would be. So that's going to be it for tonight. I need to check the calendar very quickly. I need to see, when did I say that the first drafts would be due for presentations?
Oh, it says on the 21st, 21st. Sorry.
21st. So we got
Yeah, it's a-
11 days. If that's correct, then.
Professor, also when you with the past labs that you said that you open it, but when I went through trying to redo the
Which
some
one?
questions, give me 1 second. I sent you an email. It was like 2 weeks ago. Yeah, but you said you open it for everybody.
I
And
did.
when I went through to change my answers on those, I
Is
couldn't
it the
do
black body spectrum?
No, not this one because that one is due today. So no, or last
No,
one.
the black body spectrum was due it was due the May 2nd.
Let me open my Blackboard because it's one that I have lost score on that one, and because of when I trying to.
No, Professor, it's due yesterday night.
I changed it to yesterday night because it was originally due on the 2nd, but then people were having issues with it and it was due at 10 a.m. So then I changed the due date to yesterday at midnight. And then I didn't hear until earlier today that even though I changed it, people didn't have access to it.
Professor, yeah, yesterday I tried to submit this lab and I couldn't.
Okay, I changed it. So now I addressed this at the beginning of class.
Yeah, maybe I go there to try, but I can't. Maybe
now
I
it
don't
will
know.
work. If you go there now, I guarantee you it will work.
Okay.
I had other students in the earlier section test it, so I know
It does work now.
Sorry, Andrew.
Okay.
I'm looking which one was. Okay.
All right. So you'll let me know.
I got gravity and orbits. That's the one that I have issue because I sent you an email at that time. I have in my
Perhaps I
check.
missed it.
Yeah.
I went through all my emails in the middle of the week and I responded to a bunch of.
Yeah, so on
things,
that
so-
one, I sent you an email at the time because it was too
But,
close to
yeah.
the point. So when I tried, so that's why I get lost score on that one because you had to stop in the right point and it was hard. It was a error margin like a one number. So the difference, so you can see is for example, says 8 and it was 9 because it didn't stop exactly at this right point.
Okay.
Yeah, that happened to me too on the
Yeah,
simulation.
so that's why I got lost score on that one because I'm trying to put it right there, but it was too close so you can see exactly. So you say that you're gonna change it to let it.
Yeah. Which one was that?
I got gravity and orbits. That was on April 11, and then you say that I sent you the email and you said you sent that class that you're gonna. You say don't worry about it on those.
Well, I did. I opened it up on Blackboard. But the problem is that it also needs to be opened up on my open math, and nobody had told me that. People were telling me that things were working, so I didn't change it then, but I will change it now. Now gravity and orbits, I did change to make it due June 6th. I have it extended till June 6th.
Okay, so I'm gonna try to work again because
And
last week I was
and
trying to do it
hold
and
on.
it didn't allow me to do it, nothing. So
Yeah, hold on 1 second. I see. Okay, now it's fixed. You should be able to open it.
okay, Professor, thanks.
I'm going to stop the recording.